Hello, my name is Natalie Baracaldo and I'm the manager of the AI Security and Privacy Solutions team at IBM Research Center, California. And today, I'm very happy to talk to you about IBM Federated Learning, a Python-based framework that allows you to train machine learning models among different parties without exchanging any of its training data. So, why you should care about this? Well, as a machine learning professional, you probably noticed that obtaining quality data is not as easy as it seems. In fact, your models are often as good as your training data. So if you really want to create a generalizable and accurate model, you need quality training data. So why is it so difficult to obtain training data in some cases? The reasons vary. In some cases, for instance, your model may require training data that is private in itself. In some other cases, data is protected due to regulations such as GDPR and HIPAA that make it very, very difficult to transfer and share among different places. Another case is data locality. Consider a scenario where a single company may have training data spread among different data warehouses. Transmitting this data to a single place may be very expensive and unfeasible due to its size. A final case are consortiums. In those cases, for instance, the data that you require to train a machine learning model actually resides in your competitor's company. And even though you would benefit from collaborating and creating a single model, you cannot really share that data with your competitor. All of these cases are actually a great use case for federated learning. Let's make this more tangible. For example, in healthcare, multiple hospitals cannot share their images, their X-ray images among each other to train a single machine learning model, although that would lead to higher accuracy models that would benefit both physicians and patients. In that case, federated learning could be used to train a single machine learning model without exchanging any of those X-rays. Another example where entities or parties involved may not trust each other that much could be a financial services, where multiple banks would like to train a machine learning model to detect fraud, but none of them may have enough information to create a highly accurate one. In that case, again, federated learning can help us create that model without exchanging any of the raw training data. So, how is this possible? How can we train machine learning models among different participants without getting to know any of their training data or transmit it to a central place? And the answer lies in this framework that I'm showing in the figure and the protocol that I'll explain in a second. First, we introduce an aggregator. And in the bottom of the slides, you're seeing the parties. These are, for instance, hospitals that want to train a single machine learning model without exchanging any of their X-rays. To begin federated learning, we first start with the aggregator sending a query that requests aggregated information such as weights, gradient, or sample counts to train the machine learning model. After that, the party receives the query and uses its local training data set to answer that query and sends it back to the aggregator. When the aggregator receives all the replies, it aggregates them together, creating a new model. This process may happen multiple times until a final model is computed. Here, it's important to notice that the data never left each of the parties. In fact, only aggregated information such as model weights in the case of SGDS exchange. So we have achieved what we wanted, which was not to get to know any of the private information at the aggregator side. Finally, I want to point out a little bit of terminology we use in federated learning. The process that the party ran, we call it local training, and it's symbolized by an L, and the aggregator runs what is known as the fusion algorithm. Now that we have gone through all the use cases for federated learning as well as the basic concepts, I like to dig deeper into how IBM Federated Learning works and how it was designed. When we started designing IBM Federated Learning, multiple requirements came to mind. The first one was related to data scientists who really wanted to keep using their favorite machine learning libraries. For instance, if they were already familiar with sklearn or Keras TensorFlow, they wanted to make sure that they could still utilize those libraries in order to run and start the federated learning process. From the consideration of enterprises, we also wanted to make sure that the federation from the system perspective was completely isolated from the machine learning process. With this in mind, we created IBM Federated Learning, a framework that supports the machine learning community loved libraries such as sklearn, Keras, TensorFlow, PyTorch, and RLib. And you can train a lot of different types of machine learning models in this platform, including XGBoost, neural networks, logistic regression, SVMs, K-means, and reinforcement learning. Now, I want to use neural networks as an example to show you how IBM Federated Learning allows you to train these types of model. Before we go into the code base and the Jupyter examples that I have put together for you, I like to show you the following scheme, just to make sure that we are all in the same page. So we are going to have the aggregator. The aggregator, the first thing that happens is that it's going to send the specification of the model that we are going to train, for instance in Keras, and the initial weights to each of the parties. The parties are going to train for a few epochs and send back the result to the aggregator. This is what we call a model update, and in this case, it's going to be the weights. After all the parties reply with their model updates, then we are going to aggregate. The aggregator fusions them and then keeps doing the same process by sending back the new weights to each of the parties. Each of the parties train again for a few epochs, and this process continues until the desired accuracy is reached. So now, let me show you the components of the IBM Federated Learning Framework. And here you see there are multiple modules that you can actually swap and switch at the beginning of the training process. So this is why it's important in this presentation. In the left side, you can see the aggregator stack, which is composed of a connection. For instance, you can select a Flask connection, a gRPC connection, or other type of, for instance, PubSub connection for that module. The protocol handler can also be selected, and that one is just basically managing the entire protocol. The fusion handler is the one that actually runs the machine learning and sends the queries from the aggregator to the party, waits for the parties to reply and aggregate. The party stack, it's as follows. We have again the connection, which needs to match the one that you're using for the aggregator, of course. We have the party protocol handler, which again manages the protocol, but it's slightly different because it's at the party side. We also have the training handler. This training handler needs to match the fusion handler. So if, for instance, you select the fusion handler to train an XGBoost model, you also need to select the adequate training handler for XGBoost at the party side. One of the interesting things about FFL is that we have a FL model. This FL model acts as a grabber, and it allows us to use the same fusion handler and training handler even if you switch, for instance, from PyTorch to Keras. And it's also that component that allows us to give you the ability to provide a model specification in your favorite machine learning library. And finally, but not the least, we have a data handler. This data handler is the component that allows us to basically load all the data in that party, which may be, stored in something like an Excel file or a CSV. So it's very dependent on the party and the use case. So that data handler gives us that flexibility and provides an API that is compatible with the rest of the framework. Things like preprocessing are performed in that data handler as well. Okay, so if I wanted to show you how to run this distributed system in my computer, I will use something like this terminal setup, where the big screen is running the aggregator. This other one would be running one party, and another one party would be run by this one. After starting the aggregator and the parties, we would need to register that parties into the system and follow by training by issuing a training command from the aggregator to all the parties. You can see that the system works and that we are changing the different information throughout this training process. After it finishes, we would be able to evaluate the results and see what are the accuracy and precision. However, this setup is very difficult for testing purposes since we don't have a good way to record and store all the results. So for that reason, we use Jupyter notebooks, and let me show you one in a second. Okay, so here's the Jupyter notebook that we put for you. At the beginning, we have a bunch of instructions so that you can check them online. And if we go down, we are going to see the architecture and the different components. So we have the FL aggregator on this side and the parties at the other. Here we're also illustrating the different commands that will occur during the training process. So first, the party will register, and once all the parties are registered, the cloud or aggregator is going to start the training process. And you'll see a little bit more in detail about this below. The classification problem that we are going to start here, it's actually using MNES, which is one of the simplest data sets there are for machine learning. And the idea is to classify different handwritten digits into their right number, for instance, 0, 1, 2, 3, 4, 5, 6, and so forth. So that's the data set that we're going to use. Getting things ready. So the first thing is we're importing, making all the imports and setting out our system path as it should. After that, we are going to define the number of parties that we are going to have as part of the federated learning process. In this case, we are going to use just 3. And following that, because this is an example, we want to provide each of the parties a data set that they are going to hold in order to perform the federated learning process. So now, after running this command, you can see that each of the parties has labels from 0 to 9, and that the samples in each of the classes are around the same number of data points. Once this is saved, each of the parties will have an implicit file that will be used later on in the training process. One of the first things that we need to do in order to perform federated learning is to actually define the model that we are going to train. Here in the save model specification function, we can see that we have 10 classes and we are specifying a CNN, convoluted neural network, a simple one, so that we can utilize it for training. Let's run this save command so that we can save that as H5 format. So this is a simple, using the standard Keras API, we find that file. After that, we basically need to start running that aggregator. So remember the stack I had been talking about before. The aggregator, as you can see a little bit down, has different components. And now we need to, since it's the beginning of the training process, we need to select each of these components and pass it to the aggregator. The aggregator then it's going to take this from a YAML file. And you can see the different components here. So at the beginning, we have the connection. In this case, we are going to use localhost, and the port number is going to be 5000. And additionally, we are going to use a Flask connection. The next section is the data. In this case, the data, since it's the aggregator, is optional. So if you don't have any data for the aggregator, that's completely okay. There's no need to panic. This is totally optional. But if you do, we can use it to, for instance, verify early termination accuracy of the model. After that, we have the fusion section. This fusion section tells the fusion algorithm that we're going to use. In this case, we don't want to use anything fancy since it's a little bit of an example. And I've selected ITER Average Fusion Handler. This basically takes all the model outputs of the different parties and aggregates them together. The path of that one, it's also provided in this configuration. After that, we have the hyperparameters. In this particular example, we are going to have the percentage of quorum to be 0.75. This means that the number of parties that are in total 3 could drop some of them. Number of rounds can be 30, and the termination accuracy is 0.9. We also have another section called local, and this is basically containing the optimizer and the learning rate, which is going to be that one over there. And locally, each of the parties is going to train three epochs. So basically, we are going to have 30 rounds during this example from the aggregator communicating with the parties, and then each of the parties running 3 local epochs on themselves. And finally, we have the protocol handler that we basically are selecting the very vanilla one. Okay, so with that, we can start running the aggregator. Running the aggregator is very simple. We basically pass that YAML or dictionary that we defined prior to in cell 6. And with that, the aggregator basically starts. You can see there that the Flask connection has started without any problem. Now, the next step is to initialize each of the parties. So remember that we have also a different stack for the party side. This includes the party, local training handler, party protocol handler, and a FELP connection. So this again, at the beginning of the training process, each of the party needs to takes as input a YAML file that's going to be used to basically instantiate that. And here's one such example. So at the beginning, we need to provide the party the details so that it can connect to the aggregator. Here, again, since everything is running locally, we have the local IP and the same port that we had for the aggregator. The connection for each of the parties, we need to provide a different port, and we are going to use a Flask connection. So remember that the aggregator had a Flask connection. That one needs to be matched here at the party side as well. After that, we have the data. And you may remember that at the beginning, we actually ran that command that provided a data set, a random data set for each of the parties. Now, in that NPC file, we're providing that. If your data is stored in any other type of format, do not fear. You can basically modify that MNES Keras data handler. That's what we are currently using for this example to load all the data. But if you have a database or your data is stored in any other format, you can create your own Python file that it's capable of loading that. This is just an example here, just to illustrate how this whole process works. With that, we have the local training. The local training handler, we need to load that one. This is the very vanilla one. We call it local training handler. And after that, we have the model. So remember that we had defined our CNN in Keras. Then here is where we are actually loading. So that compiled version that we save at the beginning is the one that we have here.
And finally, we have the protocol handler, that again, it's the very vanilla one. So let's run this cell so that we can go down and actually start running all the parties. So what we're going to do in this cell is basically start each of the parties. Remember that we have 3 parties, and we do that by doing party.start, and after that we are going to register each of the parties. And you can see the output in the following. This basically shows that we have a flash connection for each of the parties, and it also shows that the parties are registering. After all the parties have registered, then we are able to start the training from the aggregator. For that purpose, we have this cell over here. So what we do is basically start the training, and we're going to collect a bunch of metrics so that we, at the end of this notebook, can have some beautiful figures that tell us how the overall training process happened, and how and if the parties actually gained something from the training process. So in this output, you can see basically the entire set of requests and replies from the aggregator to the parties. And for each of the rounds, each of the parties is going to train for 3 epochs. That's the output that we're seeing right here. We kind of went with 30 epochs, which is a pretty large number for this small data set, just to produce some beautiful figures. So this is going to run for a while. One thing that I want to point out, though, is that because we are collecting the metric for each round, as you go around seeing the output, you will see from time to time what's the performance of the model in each of the parties. This type of information can be disabled if, for instance, we are in an untrusted environment. But for multi-cloud environments, this is actually very informative. So that's why we have that type of information in the output as the training process occurs. And this is going to run for a while, so we can actually relax and have a coffee. And I'll show you in a bit how the visualization results look after all these rounds and epochs have passed. Okay, so now that the training has stopped, we can visualize how the training results happen throughout. And let's run this one and go down. What we can see here is in the x-axis is the rounds multiplied by the epochs. This is the total amount of time that this run. And you can see that in the y-axis we have the accuracy. You can see that we probably could have lived with around like just 40 because we kind of reached a plateau right there. So, but it shows basically that all of the parties actually managed to have pretty good accuracy at the end of the day. We also have additional results, so let's run that last cell. Okay, and now we are seeing the results appear for each of the digits. So now we're seeing the results appearing. We can see that the average prediction of accuracy for all parties of label 0, it's pretty good. Let's see what happens for the other digits. It's also pretty good. And overall, as you can see, as we scroll down, the accuracy for each of them, it's actually very good. Basically, federated learning work. We can finish by stopping all the parties and an aggregator so that our flash connection is released. All right, so one of the interesting things about using Jupyter Notebooks is that it can allow us to run this, which in general would require to have multiple terminals. in a single place. It can be utilized to kind of help us set up the hyperparameters in a toy box if we have some data available to the person that it's really defining the model and defining the overall training process.
So now that you have seen how to train a neural network in IBM Federated Learning, I would like to also showcase another type of very different machine learning model that we can train in this framework. And this is reinforcement federated learning models. These type of models have been shown to be very useful in things like games, robotic, finance, and operation problems. And in order to be able to train one such model in federated learning fashion, the first thing that we need to do is to define the agent. This is the actor that, for instance, in a game would be a player. We also need to define the environment where that agent is going to live and the reward and cost that are associated with that agent. With that, IBM Federated Learning can really take all these definitions and start training. So let me show you briefly one of the notebooks that we put together to showcase this model. In this notebook, we show how to use IBM Federated Learning to have multiple parties train self-learning agents for the carpool problem. Reinforcement learning differs from supervised machine learning techniques in the sense that the learner isn't told which actions to take for maximizing reward. Instead, it must discover which actions yield the most reward by trying them. Now, there are several use cases, such as online portfolio optimization, robot navigation, logistic or supply chain optimization, where the reinforcement learning process could benefit from the distributed nature of federated learning. In this demonstration, we use IBM FL and RLIF to train self-learning agents for the carpool problem, where a pendulum is attached to a car with its center of mass above its pivot point. The cart moves to keep the pole upright, as shown in the GIF, and the goal is to prevent the pendulum from falling over. We begin by setting up the aggregator configuration. As before, we plug in the IP address, port number, and other networking details. The fusion handler corresponding to the model, a protocol handler to initiate the protocol, and finally, the hyperparameters to dictate the number of rounds. With these details in, we instantiate the aggregator object and start it up. Next, we do a similar configuration setup for each of the parties through the getHyperparams and getPartyConfig methods. In the getHyperparams methods, we set the training and evaluation hyperparameters for the parties. These include the checkpoint frequency, number of iterations, and learning rate, among others, for training as well as evaluation. We use the RLIF FL model class as it supports the RLIF library. The parameters, checkpoint frequency, and eager are specific to that model class. In the getPartyConfig method, we set the local training handler, the party protocol handler, networking details, and the IBM FL model class, as in the MNES example. Instead of a dataset like we had in the MNES example, in this case, we use OpenAI GIM environment for the agent. Finally, we key in the IBM FL model class to use for this run. Having done the configuration, we finally instantiate, start, and register the parties with the aggregator. With this, the Federated Learning Network is set up and the parties can begin training and evaluating the model. This takes a while, but once it's done, we visualize the results as shown. Finally, we terminate all aggregator and party process in the last cell. So I hope this demonstration was useful to understand how to use Jupyter Notebooks in the context of IBM Federated Learning. I believe playing with this type of notebooks allows you to narrow down the selection of the right hyperparameters for your data. And I would also like to point out that we keep continually working to design new fusion algorithms and to add them in the library. I invite you to try IBM Federated Learning. Here's the repo. Here are the links. And also feel free to reach out. This is my information. Thank you.